A neural network at its simplest form is just a function that consists of inputs and outputs. Each input is connected to a node via a parameter that is called a weight. These connections are known as a hidden layer. The connection of weighted inputs to nodes is where the neural network is started. The data from the inputs are then multiplied by the value of the weight parameter, x1 times w1 plus x2 times w2.
Next, there is a bias term that is added to the function. The purpose of the bias is to allow the function not to be dependent on the inputs to create specific outputs, x1 times w1 plus x2 times w2 plus b. It is important to note that the value of the weight and the bias parameters are completely random. This is to allow the computer to create different approximations of what the output will be based on the input that the computer receives. There is a problem here. With the weight and the bias being random, there is nothing to stop the computer from giving out a very large value. To correct this problem, the sigmoid function can be used, 1 minus the exponential of negative x. The sigmoid function forces the output value of the function to stay between 0 and 1. This is very helpful for the project because digital circuits operate using Boolean algebra.
The computer can now take inputs, assign random weights/biases, and provide outputs between 1 and 0. But there's still a chance of error. To eliminate this error, we will use backwards propagation. Backwards propagation is the act of the computer adjusting the random values that are assigned to the weights and biases. This is implemented by allowing the computer to compare its guess to a known correct example. In the case of this project, the changing of the weights and biases can be completed by using a cost-error function.
But by itself, it isn't quite enough. It is necessary to lower the error even more. So another function called linear regression is used in conjunction with the cost function to calculate the minimum values for the weights and biases. The code used for the project was implemented as follows. First, we needed to call all necessary libraries for all the computations needed. Then, each digital out is labeled and assigned a digital output pin from the mbed controller using the pinout diagram. Next, we needed to call all specific digital input pins for the 3 buttons used labeled X1, X2, X3. Then an array is built for the known values to propagate. This is our x1, x2, x3, and our target value. Next, the learning parameters are determined. An alpha is defined, the number of iterations are defined. Next, an array is built for all weights, biases, and random data points. Then, the sigmoid function is defined. Then the inputs are activated by calling the digital ins and digital outs, taking all the input combinations and putting them into an array. Next, the weights and bias terms are assigned to respective arrays. Next, the beginning of the training loop starts using a for loop. First, allowing the computer to pick a random data point to train. These random points are then assigned to the inputs. Next, we use the feed-forward equation, sigmoid of x1 w1 plus x2 w2 plus the bias. Next, creating an array of gradient descent and bias terms. Then backwards propagation is used. Using another for loop, we assigned updated unknown values. Then we ended the training loop by printing out all the newly trained truth tables. A while loop is then used to feed the network forward, outputting the final products of Z0, Z1, Z2, and Z3. Next, we close the while loop with a simple if statement that brings the value of Z3 to trigger the onboard LEDs.
Here you will see what it takes to build a circuit used in our project. The circuit will consist of two different logic gates. A NAND and an exclusive OR gate was used in this example. A 3-button input system was implemented. The LEDs seen are just for reference, but button 1 is the green LED, button 2 is the red LED, and button 3 is the yellow LED. The white LED you see in the circuit was used to visualize the output. The microcontroller automatically iterates through the truth table to gather the output values. The buttons were pushed individually to show the buttons actually do change the signal of the output.
Here we're demonstrating the removal of the logic gates to prove that the code did clone the input and the output of the logic gate to mimic their purpose.
Here you see the Analog Discovery 2 kit being used as an oscilloscope monitoring the output of the combination of logic gates.
From the USC's ELCT 201 family, I'm Robert.
I'm Nick.
Jordan, and thanks for watching.
And Merry Christmas.